Welcome to the topic impact stresses. So there are several types of stresses in which impact stress is the one where the member is subjected to load falling from certain height. Here in this diagram we can see that a load of W is falling from a height of let us say L onto a collar attached to this bar. And due to this fall of load W through a height of L, the bar is subjected to an elongation delta L. Then the strain experienced by the bar due to this falling load is known as impact stress. For the derivation purpose, let us take the cross section area of this bar as A and length L. Delta L is the deformation of the bar. P is the force at which the deflection delta L is produced, that is equivalent gradually applied load. And sigma I is the instantaneous stress produced due to this impact load, and H is the height through which the equivalent load P falls. We know that the energy gained by the system in the form of strain energy, that means whenever some load is applied onto the member and member gets deformed, then there will be energy stored in the member. That energy stored is known as the strain energy. Here, so the equivalent load P is making the body to deflect by a deformation delta L. Then the energy stored in the body is equal to half P into delta L. Here you can see, so this is the in the x-axis you have equivalent load P and the y-axis you have delta L. The area of this triangle is the energy stored in the bar. So that area is equal to half P into delta L, where half P is the average load applied onto the bar. And the falling load W is falling through a height, let us say H or L, whatever it is, and it gets elongated or deformed by an amount delta L. So therefore this falling load W is moving through a total distance is equal to H plus delta L. Now the energy which is lost by the weight which is falling from certain height, that means its potential energy is lost. So that potential energy is lost by the weight W is gained by the bar. So these two must be equal. Then we are equating these two, half P into delta L is equal to W into H plus delta L, and we are applying the instantaneous the equivalent load is equal to the instantaneous or impact stress into corresponding area. For P we are substituting sigma I into A, and for delta L we are writing it as delta L is equal to change in length, which can be written as stress by strain. So this is sigma I itself is the stress and strain is the change in length to the original length, and stress by strain is equal to Young's modulus. By rewriting this we are going to write this delta L is equal to stress into L by E. So now this is on the left hand side. On the right hand side you have W, H, and delta L is written in the same form, that is sigma I into L by E. By simplifying this equation we are writing a quadratic equation, and this quadratic equation is in the sigma I. So AL by 2E into sigma I whole square minus WL by E into sigma I minus WH is equal to 0, and the roots of the quadratic equation gives the plus or minus, but we are interested more in the plus, the positive amount of stress that is produced. That means because load is applied on the bar and the bar gets stretched. When bar gets stretched, it is subjected to tensile stress. So therefore, we are interested in finding the tensile stress rather than the compressive or negative stress. So that is W by A into within the brackets 1 plus square root of 1 plus 2 HAE by WL. So this is the formula derived to find out the impact stress. Let us take a simple problem. An unknown weight falls through a height of 10 mm, so it's very small, onto a collar rigidly attached to the lower end of a vertical bar of 3 meters long, 600 mm square in cross section. If the maximum instantaneous extension is 2 mm, what is the corresponding stress and the value of unknown weight? So here we have to find out the two things. One is the stress that is developed in the member which is causing the extension of 2 mm and the corresponding weight. Let us take the Young's modulus for the bar is 200 kilonewton per mm square. So the given data is written. The height through which the weight falls is 10 mm, only 10 mm, and the length of the bar is 3 meters, that is 3000 mm. The cross sectional area of the bar is 600 mm square, and the extension of the bar under the influence of the load is 2 mm. Young's modulus is 200 kilonewton per mm square, or it can be written as 200 into 10 to the power of 3 Newton per mm square. First let us write the Young's modulus, that is stress by strain, and we can write it as in terms of stress and the change in length delta L, that is stress into L by delta L, and we rewrite this as stress is equal to sigma E, that is Young's modulus into delta L divided by L. So here the Young's modulus is 200 into 10 to the power of 3 and delta L is 2 mm and the length of the bar is 3000 mm. So we got the instantaneous or the impact stress in the member is 133.3 Newton per mm square. And the unknown weight, that means the weight is falling from 10 mm and it causes a extension of 2 mm, but the weight of that is not given. So we need to find out that weight. So to find out that weight, we are using the expression derived. The impact stress is equal to W by A into within the brackets 1 plus square root of 1 plus 2 HAE by WL. So we need to find out this W, the weight of this falling weight, the value of the falling weight. So W we need to find out. The other things are known. Impact stress is 133.3, that is 400 by 3, and cross section area 600, and H, height through which the load W falls is 10 mm, cross section area of the bar once again 600, and the Young's modulus is 200 to 10 to the power of 3, and the length of the bar once again it is 3 meters or 3000 mm. By solving this for the value W, we got the W as 6666.7 Newton. So we have found out the two things. One, the stress induced in the bar, and second one is the weight of the value of the weight that is falling through a height of 10 mm, which is causing a deflection of 2 mm. Next, resilience. So whenever a body is loaded within the elastic limit, we know that it changes its dimension, and on the removal of the load it comes back to its original state or restores its original dimensions. So long as it remains loaded, some amount of energy is stored in the member, which is known as the strain energy. The strain energy has always capable of doing some work. The strain energy stored in the body due to external loading within the elastic limit is known as resilience. What is resilience? Resilience is the strain energy that is stored in the body within the elastic limit, and the maximum energy that can be stored in the body up to that elastic limit is known as proof resilience. So resilience is the one which is within the elastic limit. It's not up to the elastic limit. If you take up to that elastic limit, the amount of energy that can be stored in the body is known as a proof resilience. The proof resilience per unit volume of material is known as the modulus of resilience, and it is very important property for a material which gives the capacity of the material to bear impact or shocks. So this is a very important parameter in designing of elements which are subjected to the shock loads or which are subjected to loads falling from certain height. Mathematically, the strain energy stored in the body either due to the tensile or compressive loads is equal to, it is designated by the capital U, and capital U is equal to sigma square by 2E into V. Sigma is the impact stress, and E is the Young's modulus, V is the volume of the member, cross sectional area multiplied by the length. When the body is subjected to the shear load, this is either due to tensile load or due to compressive load, whereas for the shear load we have to replace the sigma square by 2E with the tau square by 2C, because sigma is for normal stress and tau is for the shear stress, and E is the Young's modulus and C is the rigidity modulus. When the body is subjected to torsion, this is simple shear, whereas this is for the torsion, then the modulus of resilience is tau square by 4C. Let us take one more simple problem to understand the concept of resilience and strain energy stored in the body. A wrought iron bar 50 mm in diameter and 2.5 meter long transmits a shock energy of 100 Newton meter. Find the maximum instantaneous stress and elongation. Take Young's modulus is 200 giganewton per meter square. The given data is the diameter 50 mm, length 2.5 meter, that is 2500 mm. Strain energy stored U is 100 Newton meter. It can be written as 100 into 10 power 3 Newton mm. Young's modulus is 200 giganewton per meter square, which is same as 200 to 10 to the power of 3 megapascal or Newton per mm square. And first let us start with the maximum instantaneous stress or the impact stress. So impact stress, to calculate that we use the expression, the sigma is equal to the strain energy is equal to sigma square by 2E into volume, for which you need the strain energy 100 into 10 to the power of 3 and volume. The bar is having a diameter 50 mm and length 2.5 meter. The volume is calculated pi by 4 d square into L, so which comes out as 4.9 into 10 to the power of 6, that is volume, and Young's modulus is 200 into 10 to the power of 3 Newton per mm square. On substituting these the unknown value, the instantaneous stress or the impact stress in the member is equal to 90.3 Newton per mm square. And now let us find out the elongation produced when the strain the member is subjected to some amount of force and that resulted in stress, and the stress is found out, the stress is producing the strain in the member, or in other words, member is subjected to load and load tries to deform the member, and the resistance offered by the member to the deformation is resulted in stress. That means whenever you have a stress in the member, that means you can assume that it is subjected to some amount of strain. So that strain and the corresponding change in length we can calculate from the expression. The Young's modulus is equal to stress by strain, and from that you can write strain is delta L by L, change in length to original length, and we need delta L. So for delta L we write sigma into L by E. So sigma is the stress 90.3 and L is 2500 mm and Young's modulus is 210 to the power of 3. So that comes out as the change in length or elongation produced in this case is 1.13 mm. Now these are the problems for practice. Students, please take note of these problems and solve on your own. The first problem is a bar of 2 meter length, 20 mm breadth and 15 mm thickness. This is not circular in cross section. This is rectangular in cross section. It is subjected to a tensile load of 30 kN. Find the final volume of the bar if the Poisson's ratio is 0.25 and Young's modulus is 200 giganewton per meter square. And next is a bar of 12 mm diameter gets stretched by 3 mm under a steady load of 8 kN. What stress would be produced in the bar by a weight of 800 Newton which falls through 80 mm before commencing stretching of the rod, which is initially unstressed. So the rod was unstressed, but due to the falling weight of 800 Newton through a height of 80 mm, that starts or initiates or commences the stretching of the rod. The first one is a simple stress case and second one is the impact stress case. So find out the required things from the problem 1 and problem 2. So these are very helpful for you students, and solve these problems and we will meet in another lesson. Thank you.